We are all bombarded with flux of extremely tiny particles which pass through our bodies uninterrupted and unnoticed. Tens of trillions of them are passing through our bodies every second. These ubiquitous particles called neutrinos are extremely light and extremely fast. They travel with speeds which are very close to the speed of light. After photons, neutrinos are the most abundant entities in this universe. Since neutrinos have no electrical charge, they interact very weakly with matter, and it is really hard to detect them. Trillions of neutrinos pass through every square centimeter of Earth every second without any interaction with matter. These mysterious particles are nicknamed ghost particles. The Standard Model is the theoretical framework for explaining elementary particles that constitute matter in this universe. According to Standard Model, all matter is made of 12 elementary particles called fermions. These fermions are classified into quarks and leptons. The lepton family consists of electron, muon, tau, electron neutrino, muon neutrino, and tau neutrino. We see that there are three types or flavors of neutrinos. Since neutrinos do not have any electrical charge, they are not influenced by the electromagnetic force. They interact only through the weak force and the gravitational force. Neutrinos are present all around us, coming from various sources. The earliest neutrinos produced in this universe originated within 1 second of Big Bang. These primordial neutrinos are still remaining in the universe, and there are 300 of them in every cubic centimeter of space. Most of the neutrinos reaching the Earth are solar neutrinos directly coming from the Sun. These neutrinos are produced in the fusion reaction taking place in the core of the Sun. Hydrogen nuclei are fused into helium nuclei in the core of the Sun, releasing energy in the process. Neutrinos produced in this process reach the Earth before light produced in the same process reaches Earth. Since neutrinos barely interact with matter, they are able to escape from the core of the Sun immediately after they are produced. Photons bounce around within the core before they can escape. Atmospheric neutrinos are produced by the interaction of cosmic rays with the atoms of the atmosphere. Cosmic rays are energetic particles coming from space. When they strike atomic nuclei in the atmosphere, there is a cascade of particles among which there are neutrinos. Neutrinos reaching the Earth from stars other than the Sun have very low intensity due to the enormous distances involved. But we can distinguish neutrinos from supernovae explosions. Stars many times more massive than the Sun can explode into supernova. In a supernova explosion, enormous amount of energy is released. A whopping 99% of this energy is carried away by a burst of neutrinos. Neutrinos coming from inside the Earth are called geoneutrinos. These geoneutrinos are emitted by naturally occurring radioactive nuclei within the Earth. Decay chains of uranium and thorium are major sources of geoneutrinos. There are two major sources of artificially produced neutrinos: particle accelerators and nuclear reactors. Intense beams of neutrinos can be produced by particle accelerators. Protons accelerated to velocities very close to the speed of light are made to hit a target of beryllium or graphite. In the process, neutrinos are produced. Nuclear reactors are convenient sources of neutrinos for experimental studies. In a reactor, the nuclear fission leads to the generation of neutrinos. In nuclear fission, a very heavy nucleus splits into two moderately heavy nuclei which are called fragments. These fragments undergo decay chains to achieve stability, and neutrinos are produced in this decay chain. Our understanding of neutrinos started in 1930 when theoretical physicist Wolfgang Pauli suggested the need for a new particle to explain radioactive beta decay. At that time, beta decay appeared to break the law of conservation of energy. In beta decay, a neutron is transformed into a proton and an electron is emitted in the process. According to the law of conservation of energy, the electron should have a definite value of energy. But all experimental measurements showed that the electron was taking a range of energies instead of a single value. Pauli proposed that another particle was also emitted in the process along with the electron, which shared the energy of the process with the electron. Pauli called this new particle neutron. He admitted that this was a desperate remedy to save the law of conservation of energy. In 1932, James Chadwick discovered the particle which we now call the neutron. This was much heavier than Pauli's proposed particle. A year later, in 1933, Enrico Fermi formulated his theory of beta decay, or the theory of weak interactions. In this theory, the particle proposed by Pauli played an important role. Enrico Fermi renamed this particle as neutrino, meaning little neutral particle. Though the neutrino was a perfect fit into the theoretical scheme, nobody could actually find a neutrino for the next quarter of a century. But the search was on. In the 1950s, two scientists at the Los Alamos laboratory in USA set out to find the mysterious neutrinos. Frederick Rains and Clyde Cowan set up an experiment to find neutrinos. The search for the mysterious ghost particles was named Project Poltergeist. They set up a neutrino detector near a nuclear reactor at Savannah River in South Carolina, USA. In 1956, Rains and Cowan made history by observing neutrinos for the first time. These were antineutrinos emitted from the fission reactor. The detector had 400 liters of water with cadmium chloride dissolved in it. The antineutrinos interacted with water, producing neutrons and positrons. Annihilation of positrons with electrons produced gamma rays, which were detected by scintillators in the detector. The neutrons created were absorbed by cadmium, which also produced gamma rays. These gamma rays were detected separately. In 1995, Frederick Rains was awarded the Physics Nobel Prize for his work in Neutrino Physics. The neutrinos observed by Rains and Cowan were electron neutrinos. The separate identity of muon neutrinos was established in 1962. The third kind of neutrinos, the tau neutrinos, were discovered only in 2001. The Kolar Goldfield experiments in India identified atmospheric neutrinos in 1965. Experiments led by Ray Davis at Brookhaven National Laboratory in USA identified solar neutrinos for the first time in 1968. The first observation of neutrinos from a supernova was done in 1987. The Kamiokande detector in Japan and the IMB experiment in Ohio, USA identified neutrinos coming from the supernova explosion 1987A. This event occurred some 150,000 light years away in the large Magellanic Clouds, the galaxy nearest to the Milky Way. These neutrinos were identified on Earth 3 hours before light from the same explosion reached the Earth. This event marked the beginning of neutrino astronomy. Of all the fundamental particles, neutrinos are the least understood ones. For half a century, physicists thought that neutrinos, like photons, were massless entities. The standard model of particle physics treats neutrinos as massless. But experimental evidence now shows that neutrinos have mass. The fact that neutrinos have mass was revealed to us through the successful solution of the solar neutrino problem. Of the three flavors, only electron neutrinos are produced in the thermonuclear fusion reaction in the Sun. From solar luminosity models, it was calculated that 70 billion neutrinos from the Sun should reach every square centimeter of Earth in every second. But experimental observation showed that only a third of the solar neutrinos predicted by the solar luminosity models actually reached the surface of the Earth. The mysterious disappearance of the remaining electron neutrinos became a puzzling problem for the scientists. This is known as the solar neutrino problem. In the late 1960s, the Homestick experiment by Ray Davis and John Bacall was the first to measure solar neutrino flux. and detect a deficit in the number of electron neutrinos reaching the Earth. The experiment took place in the Homestake gold mine in South Dakota, USA. Ray Davis and Masatoshi Koshiba won part of the Physics Nobel Prize in 2002 for experimentally establishing that only a third of the solar neutrinos predicted by the models actually reach the surface of the Earth. Masatoshi Koshiba's experimental studies were instrumental in establishing neutrino studies and neutrino astronomy on a firm footing in Japan. The solar neutrino problem was solved by improved theoretical understanding about the properties of neutrinos and sophisticated experimental methods. According to the standard model, there are three flavors of neutrinos: electron neutrinos, muon neutrinos, and tau neutrinos. Standard model treats all of them as massless. Only electron neutrinos are produced in the sun, and experiments like Homestake could detect only electron neutrinos. In 1968, Italy-born Soviet nuclear physicist Bruno Pontecorvo suggested that if neutrinos had mass, then they could change from one flavor to another. Then the missing solar neutrinos could be electron neutrinos transformed into other flavors of neutrinos. These other flavors could not be detected by Homestake and the other early detectors. Pontecorvo's brilliant ideas were not immediately accepted by the physicists, mainly because it went against the standard model. In 1998, the Super Kamiokande experiments, led by Takaaki Kajita, announced the first evidence for neutrino oscillations. Neutrino oscillation is the transformation of one flavor of neutrino into another. The Super Kamiokande detector consists of a stainless steel tank filled with 50,000 liters of water. 13,000 photomultipliers are surrounding this huge tank. The detector is located in the Kamioka mine in Japan. The Super Kamiokande team looked for neutrinos which were produced when cosmic rays interacted with atmospheric atoms. These atmospheric neutrinos are mostly muon neutrinos. When these neutrinos pass through the detector, they interact with the atomic nuclei in water to produce electrons, muons, and tau particles. When these particles travel in water, they produce Cherenkov radiation. These Cherenkov radiations are identified by the photomultiplier tubes surrounding the tank. The Super Kamiokande detector could record neutrinos coming directly from the atmosphere above, and also the neutrinos coming after passing through the Earth from the other side. The observation showed that about half of the neutrinos reaching the detector after passing through the Earth were lost, while the neutrinos coming directly from the atmosphere above were not. The only possible explanation is that a portion of the muon neutrinos are getting transformed into tau neutrinos while passing through the Earth. This is a definite indication of neutrino oscillations. Further observations at Sudbury Neutrino Observatory in Canada definitively established neutrino oscillations. Sudbury Neutrino Observatory SNO is a neutrino observatory situated 2,100 meters deep in a mine in Sudbury, Canada. It was designed to observe solar neutrinos with the help of a detector consisting of a tank filled with 1,000 tons of heavy water. SNO could observe all three types of neutrinos collectively and electron neutrinos exclusively. After extensive statistical analysis, SNO scientists showed that only 34% of the electron neutrinos starting from the Sun reached the Earth in the same flavor. The 2015 Physics Nobel Prize was awarded to the scientists who led the experimental teams at SNO and Super Kamiokande, Arthur B. MacDonald and Takaaki Kajita. The discovery of neutrino oscillations challenged the standard model's assumption that neutrinos are massless entities. A massless particle travels at the speed of light and it cannot change from one form to another. Neutrino oscillations establish that neutrinos change from one flavor to another. The only conclusion is that neutrinos have mass. but the masses of the three flavors of neutrinos are yet to be determined. The standard model of particle physics now stands as an incomplete theory. Theoretical and experimental research into the properties of neutrinos are in the forefront of scientific research today. An improved understanding of the properties of neutrinos can give answers to many of the puzzling questions about the universe as it exists today.